Alright, welcome to our video walkthrough of day 20 from Advent of Code last year, 2021. We've got new Advent of Code problems coming up in about a month or so, but for now we're still just getting warmed up for that by going over some of last year's problems. And this problem is sort of this image enhancement problem. The first line of our input is a 512 character string. Everything in here is binary, where the hashtag is a 1, the dots are 0. And so this first line is a key. Tells us essentially, well, I don't know. We'll get to exactly what the key means later as we're implementing the algorithm. Basically, we want to take this 2D image and we want to expand it. And we'll just do a series of expansions. And the way we expand it is basically for each individual pixel, we take the 9 pixels or the 8 pixels around it, and we can convert those into a binary number, and then we index into the binary number based on this decoder key. So we just have to run a certain number of expansions, and we have to figure out basically how many of these pixels are lit, how many of them are turned on or just after the final step. So that's basically our goal here. There are a couple nuances that we'll discuss as we go along, but let's just go ahead and get started with parsing our input. So a few different stages to this. First, we want to just parse a single bit, and that's actually pretty easy. We want to use choice. So choice allows us to essentially pick between 2 different parsers. If the first one fails, we'll just go to the second one, and you can actually even add more than that. You can get a whole list of them. So the first one, we'll try reading a character that's just a period character. This will have us return a 0 bit. We're using our binary bit type from last time. This is what we're using to represent everything in our image, and this is a really simple parser that'll let us get going with that. So if we have the hashtag, then we get a 1. Now, what are we going to do with these bits? Well, we have 2 different parts of this. Obviously, we have our decoding string that we're going to, or we'll call it a decoding map. Decoder maps. This is just to be a hash map from the index to the bits. I suppose actually a vector may have been a better idea here, but I just ended up using a hash map just for fun. The image map is where we really do want some kind of a map where we'll we have our 2D image, and we want so we have 2D coordinates, and then each of those is a bit. So that's where we will start. We want to get this decoder map all parsed and everything. So that's actually what we can start with. Is we can have our parse input function. This will return the decoder map and the image map that we have in our file. So the first thing we can actually do here is that we can go ahead and parse just some of these pixels. That's our first line. And if we want to build the decoder map, the one that we can return, all we have to do is map this build decoder function onto it. So build decoder. And now we've already got our decoder map. We're off to a great start here. So now the next thing we need to do is we need to parse 2 end-of-line characters because there is an empty space. So we have the end of line for this first line, and then we have an empty line on 2, and then we get to the 2D image. So for that, we'll have this parse 2D image function. This will give us the list of bits, and that's actually follows a familiar pattern that we've been using here. So we'll parse pixel, set n by 1 with the end of line separator. That basically has been our ticket towards parsing these lists of lists, except instead of parse pixel, we need some parse pixel. We need to get a whole series of those. So you can start getting the image if we say, okay, image, let's parse 2D image. But like I said, we want a hash map. We don't, we don't want to simply be returning a nested list. And so there's this utility function. It's actually where I put it here. Yeah, here it is. Hash map from nested lists. And this just lets us take our nested list and turn it into a hash map. Just Really simple thing there. So let's go ahead and write it out. So hash map from nested list. Let me map that over a decoder map image, and I think that's right. That may not quite that. I didn't quite spell it right. There's a nested list. Okay, yeah, I did spell my value correctly. Okay, so I think that might just about. Oh yes, we need to fill in build decoder. So we use this function here to convert our list of pixels, our list of bits, basically into the decoder map. Again, it would, if we used vector would actually end up being simpler here. But hash map also works fine. I'll just stick with it because that's what I did on my first pass of the problem. So we just we zip with all the numbers on input, and we just make that into a list of tuples and create our hash map from that. So that pretty much resolves parsing the input. It's not terribly complicated input. So now we want to do the algorithm. The algorithm gets a little complicated, mainly because of this argument. And I guess I'll bring up the problem definition because it illustrates this a little better. But basically, we're gradually expanding our image and enhancing it, and it gets bigger each time, takes up more space. But we have all these other pixels that are technically part of the image. And for it is possible that these will also change. In fact, in one of our decoding keys, the one that we actually have for the big part of this problem, what we see is that this first character is on. It's the hashtag, it's the pound sign, which means that empty pixels surrounded by other empty pixels turn on. And so that does some weird things where we need to, they will keep flipping on and off because the first one over here is on, and then the end of this is off. So that means when it's a on pixel surrounded by other on pixels, it turns off. So everything else basically keeps flipping on and off. So that's what this extra bit argument is in these two helper functions. We're going to build our algorithm from the bottom up, but we need this extra bit here. I call this the outside bit. And that just tells us, okay, things that are outside of our current map, what bit are we going to use for those? So basically our overall process, we have run expand. This will take a certain number of steps, take the decoder image in the image map, evolve the image map to its final state, and then return the number of lit pixels in that final state. So one step of the algorithm will be expand image, and then within expand image for each of the different pixels in the new image map that we're creating, we're going to say process pixel. So that's sort of the flow of this problem. I'm going to start with process pixel, just do this from the bottom up. I've already laid out these type signatures. The main thing we want to see here is that this is going to be a fold. We're going to provide these three arguments, partially apply them to this function, and then we can use the rest of it in the fold. So we have image map, chord to image map. So we follow that A to B to A pattern that you want if you're doing left fold. So let's just have our arguments here. So we have the decoder map, we need that. We need the initial image as we process the pixels, and then we need our outside bit. And then we have the new image that we're trying to build. We are gradually inserting new characters into this new image map. So that's how we're folding this. We'll see how that works. And then we have pixels. So this is the specific coordinate that we're dealing with here. And what do we do? So first thing we need to do is we need to get all the neighbors of this pixel. So we say all neighbors, and we're going to use this function, get neighbors 8 unbounded. And if you watch the octopus problem, we had this neighbors 8 idea where we have a single coordinate and we look all around it for the neighboring coordinates. With unbounded, we actually remove the sort of bounds we put on it, where originally we would say, okay, we only want between 0, 0 and the max row, max column. Because we keep expanding our image, there are no bounds on the coordinates we're going to use. We're going to allow ourselves to have negative coordinates. And that's actually, it's really cool that we're doing this in Haskell, because Haskell just really easily and really natively allows us to have hash maps that have negative indices. Whereas if you were doing this with a conventional array, in a Java or C++ language, things would get a little messy with trying to keep track of which index you're on. So this is actually really easy for us. So we're going to get all of our neighbors. We want to get the bits associated with those neighbors, so neighbor bits. And, well, obviously we need to loop some function over all neighbors. I'm going to call that getBit, and we have to define what that means down here. So what is getBit? GetBit takes a single coordinate and returns the bit associated with that coordinate. What happens here? So we want to take our initial image and we want to do just a normal hash map lookup on that coordinate, but we're doing it maybe because the points on the fringe that are right outside, those are not in our hash map. And so we'll get out of bounds, but when we account for that, we say from maybe, and then here we're using our outside bit. So our outside bit acts as a default whenever we're retrieving a bit from a particular neighboring element. Now we do expect we will always have 8 neighboring elements. So if it's not equal to 8, we're just going to have an error there. If I wanted to be really precise, I would probably, just because of this error case, I would wrap this in like maybe T or something, but I just ended up not doing that for this problem. Otherwise, so we're in our success case, but we have to split them up. We have to say first for and second for. We'll say split at on those neighbor bits, and then we're going to make a new set of our final bits because we need all 9. In order to decode and expand this pixel, we need all 9 values, including the pixel itself. So we have getBit on this pixel. That's sort of the one we need to add. So we'll append that in front of second for, and we'll say first for plus that. And now we get our, now that we have all 9 of these bits, we can actually index into our decoding key. So we'll say index to decode bits to decimal 64. We're just using this other utility that we had actually last week in the binary packet parsing problem, where we just convert a list of bits, binary essentially, into a decimal number. That gives us our index, and then we're pretty much done here. We just say we're going to insert into our hash map this particular pixel with this particular bit. We're going to do that into our new image, except where did I get? I need to say bit is equal to decoder map. Again, that actually look a lot cleaner if I use a vector instead of a hash map. But well, initial image, just initial. Okay, so this function's done. So this tells us how to process a single pixel. Okay, now let's expand the whole image. Let's get all of the pixels. So again, this takes a very similar set of arguments. So decoder map, image, and the outside bit. And what are we doing? Like, our ultimate goal is to do a fold. We're really a fold M because we're doing this monadically. So in order to make this fit the pattern of fold, I'm actually going to keep these sort of hints around so that we can see how everything fits in. We want this to be some variation of process pixel, but we need to partially apply this argument, and this argument, the first 3. So we'll say process pixel, decoder map, image, outside bit. We need our initial value, which is just an empty hash map. When we first start creating the new image for the next level, it starts out as empty. And then we need the coordinates. So we need all of the coordinates, all of the pixel coordinates that are going to be in the new image. And that's actually more than the pixels that are in the old image. So we'll get, for example, okay, min row, min column is equal to the minimum of the keys in our current image. Similar to this, I guess that doesn't work. Okay, so we'll also get the max row. And so our new bounds, we're going to have 2 different tuples for these bounds. So say min row minus 1, we're expanding in that direction. Min row minus 1, min col minus 1, max row plus 1, max col plus 1. These are the new bounds. And so to get all of the coordinates, we have to take a range of these new bounds. So this essentially interpolates all of the different coordinates between these two coordinates. So really helpful function from data.index. And this is our complete definition for expanding the image. Now run expand, we'll call expand image. It'll recursively do it step by step. We have this counter argument so that we know how many steps we're doing. The first step, we imagine we have an image and we're at step 0. So we're ready to return something. So return will count where just everything and where it's 1, the bit 1 in the elements of our image. Simple base case, recursive case, decoder map, initial image, and the step count. Okay, what are we doing here? First, we have to call expand image, obviously. It's the main thing. So we'll say final image comes from expand image. Obviously, we pass decoder map, initial image, and we need to calculate what the outside bit is. That's the tricky part here. So what's outside bit? So if the decoder map at 0 is 0, if we plug in the 0 bit, then we're always going to just return 0. What's our other one case? Our one case, so if the step count is even, then the outside bit is also still going to be 0, because they start off and then they flash on during the odd counts, and then go back to off for the even counts. So that's how we calculate that outside bit. And now we're done. Now we're ready to recurse. We'll say run expand decoder map final image, and then we'll subtract 1 from the step count. And we're just about done here. We just need to fill in Boolean. So we'll parse our inputs. So how many pixels are lit? We just call our run expand function, pass our arguments. For the easy part, we're just running 2 steps, and we'll return number of pixels lit. Not list. I suppose I could simplify that if I wanted to, but now the second part, same thing basically. We're just doing 50 steps. And now we can go ahead and run our code. So we can do day20, easy, small, 35. I think that's the correct answer. So 35, 58, 19. Those are our 2 answers. So what's the big case? 58, 19. Now we'll notice this is taking a second, and this is maybe the first problem I've run into, where it's like it's taken a second. It's not. I'm not doing this totally inefficiently, but it is a noticeable amount of time to get the answer, especially on this last case. We'll say 50 steps on our very large solution. This might take a couple minutes. But we are getting the right answers. And I'm not sure exactly how I would optimize this off the top of my head. I mean, using a vector instead of hash map probably wouldn't get that much, benefit. There are maybe some clever things we can do with like caching the values in bits, so we're not always doing all of these lookups. So if you really optimize, you could try and do that, but we still get our answer in. I think that was less than a minute. So that's not too bad, but at least we're getting the right answer, and it's not taking too long. Towards the end, you'll see this with How Advantage Code. The problems get harder, and they get harder to do accurately and efficiently. So this is kind of natural. And you know, I'm not necessarily the best at this, so it's not uncommon that my solutions aren't the most efficient. Bunch of debugging stuff. Our tests are now going to take a little bit longer to run just because it's running the 4 tests for day 20, but they should all come back as correct. And everything is good. So that's all for this video. Next week, I think we'll be doing one more problem from last year's Advent of Code, and do make sure that you subscribe to Monday Morning Haskell newsletter. Link for that is in the video description. After next week's episode on this sort of video blog series, I guess be having some special offers that will be going out to our subscribers, so you do want to make sure that you are subscribed to the newsletter. If you want to see the code for this episode, that is also linked in the description, as well as the write-up that I did in the blog earlier this week. So thank you so much for watching, and I will see you next week.